Welcome, thanks for being here. It's a good choice to be here. Let's talk some calculus now. Get yourself prepared, grab a notebook, a pen, or a pencil. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. Today we've got a problem from the 2007 AP Calculus BC exam. That being said, I don't think there's anything which requires a BC technique specifically. No? So if you're an AB, you can totally approach this problem. Very doable. Go ahead and give yourself, 12, 15 minutes or so. Read through the problem, give it a shot yourself. Pause the video while you do that, and then when you're ready, come on, join back and see how we walk through this. Maybe pick up some skills along the way, or check to see if you're on the right track. Alright, we're going to start off by analyzing this problem. This is a kind of a related rates meets integration approximation problem. We're given a chart. It's r prime. R is usually the radius, so some kind of radius, and r prime means the change in radius. We see feet per minute. So how fast is the radius changing of something? Let's read through the problem. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. Hey, yeah, ideal gas law, right? Chemistry people. The radius of the balloon is modeled by a twice differentiable function, r of t. T is in minutes, right? As we see here. From 0 to 12, the graph of r is concave down. That's probably going to come in handy like later. And the table gives selected values of the rate of change, which is r prime. Yeah, tells us how fast. Oh, and here they give us an initial condition. The radius of the balloon is 30 feet when t equals 5. So actually I'm going to put that right here because this chart tells us the speed at which the radius is increasing, how fast the radius is changing, but that gives us the actual radius at that point. So we're probably going to have to use the initial condition somehow. All right, let's take a look at part A. Oh, and they gave you the volume of a sphere with a radius of 4/3 pi r, yada, yada, yada. You got to know that. You should know that. The volume of a sphere. You should know that formula. Okay, let's get started with part A. They want us to estimate the radius of the balloon when t equals 5.4 using, they gave us what to do. Use the tangent line approximation. So we're just going to use this information here, which is the derivative and the radius at that moment, and then approximate somewhere close. Oh, and they also want us to indicate, is your estimate greater than or less than the true value? Okay, so tangent line approximation means I should write this out. I'm going to write it in the y minus y1 format, but I'm going to put r. So it's like r minus the r value equals r prime, the slope, times t, that's a very crooked t, t minus our t value. The t value at point of tangency is 5. So we have r minus 30 equals something times t minus 5. That is going to be the derivative 2.0. So now we're going to plug in the time of 5.4 because that's where we want to approximate. We know that it's equal to 30 at 5, but we want to use this slope since we don't have information at 5.4. We're going to use this closest point to approximate. So this is going to be r minus 30 equals 2 times 0.4. So that's 0.8. R equals 30.8. We can say that it's increased by approximately 0.8. according to how much it was going at that time. Now, the second part of this question is asking if that is an over or underestimate, if the estimate is greater than or less than. And here already we're going to use the fact that r is concave down, because that means the graph of r, roughly looks something like that. And we have the exact amount here at 5, and we're trying to estimate it a little further at 5.4. But you'll notice that any one of these estimates that I draw, maybe I'll use a different color for this. Any one of these tangent lines on a concave down function is going to be an overestimate, right? So that's going to overestimate any value further down the line at 5.4. The true value is down here, but the tangent line is sitting on top, so it's going to suggest that it's a little higher than it is. So this is going to be greater than the true value. And that's because r double prime is positive. Sorry, negative. It's concave down. Okay, yeah, good. Let's look at part B. Find the rate of change of the volume with respect to time when t equals 5. Okay, that's not bad. I mean, they did graciously give us the formula. It's right up there, 4/3 pi r cubed. Should already know that, though. And that means that the derivative dv dt is going to be 4 pi r squared, and don't forget the implicit step, times dr dt, or times r prime, if you want to call it that. And at the moment when t equals 5, this is simply 4 pi times 30 feet squared. I didn't really put the units, but it's fine. Times the derivative at that moment, which is 2.0 feet per minute. This is pretty easy to calculate. 30 squared is just 900. Times 4 is 3600, times 2 is 7200, times pi is 7200 pi. Now the units, it's important. They said indicate units. That means you get a point for the units. Don't lose points just because you didn't put units. It's a change in volume, which is cubic feet per minute. Bam, like that. That one was pretty fast. Just a very straightforward use of the derivative relationship, the related rate. Okay, part C. Use a Riemann sum, a right Riemann sum, that is, with 5 subintervals. Okay, they gave us that, so that's good. Indicated by the data in the table to approximate integral from 0 to 12 of r prime. Using correct units, explain the meaning in terms of the radius of the balloon. I can explain that right now, actually. So r prime tells us the change in the radius over a small amount of time. If we look at that over a long period of time, we get the total change in r, because r prime is a small change over a small time. If we add up all of those small changes, we get the total change in r, and the units is going to be in feet, of course, over the 12-minute period. Yeah, so the units are right there in feet. Now we have to actually calculate it using right Riemann sums. So we're going to say that the integral from 0 to 12 of r prime is approximately, well, let's say the first rectangle has a width of 2 and a height of 4.0, because I'm using the right side endpoint for the height. So 2 times 4, easy. The next rectangle has a width of 3 and a height of 2.0. We've been using that one. Pretty easy stuff. Then the next rectangle has a width of 2 and a height of 1.2. Okay. Then the fourth rectangle has a width of 7 to 11 is 4 and a height of 0.6. And then lastly, we have this fifth rectangle with a width of 1 and a height of 0.5. So let's see, adding this all up, we have 8 plus 6 plus 2.4 plus another 2.4 plus 0.5. So let's see, 10.8, 18.8, all right, 19.3. 19.3 feet. I believe that's right. Let's see, this is 10.8, so that's 11.3. So yeah, 19.3 feet. That's how much the radius changed by over that 0 to 12 minute period. And we already explained what it represents and as well the units. And we used the units again there, so we're good. Part D. Okay, another question about this greater than or less than the true value. Is your approximation greater or less? That's a good question. Well, for r, we know that r was concave down. So r was shaped something like this. But we were adding up rectangles with r prime to approximate the change in r. And if you look at r prime, I mean, you can even look at it through looking at r. The slopes are getting less. They're positive, but they're getting less. So it's going to start like here and be going down somehow. You can confirm that by looking at the values of r prime. And that's what r is concave down means. It means that the derivative is getting less. So the derivative's going downwards. That means that if we make rectangles, these left-handed rectangles would all be sitting on top of the curve, overestimating. But any right-hand rectangles of any decreasing function is always going to be an underestimate. Even if it was concave down, even if it did something like that, these would still be underestimates, right? So as long as it's going down, r prime is going down. So we can say r prime is decreasing. Therefore, we are underestimating the area underneath it to change in the radius by using right rectangles. If we use left rectangles, we would totally have the exact value. By approximating with right rectangles. Okay, and that's just giving like a full explanation, a full reason why. Now, some pitfalls here. Chart problems, you're generally going to be approximating stuff because we don't have an actual function equation. We just have chart values. And this one was kind of clever that they combined the idea of related rates. When we found the volume, we have to just use the chart as part of the derivative of the volume. And then really being aware of under or over approximations. How do we know if it's an underestimate or an overestimate based on the function, based on the shape of the function? And last but not least, don't forget units in a problem like this. That's probably the silliest thing to miss points on. So when they say use correct units, it's because you can get 1 out of the 9 points removed by not including units. So we have them there, and then we stated them twice for part C. Okay, that's enough blab out of me. See you guys next time in the void.